Hello. Testing.
Yeah, another chap wanted to make a comment. I was looking through my electronics library, and we were talking about electronics courses or something, and thinking I was two books there from Australia posting their teaching electronics and electricity principles. So they're very old books, but you can have a look at them.
Ah, these.
Yes. So they were being thrown out in the rubbish bin, and I decided I'd collect them and share them. Well done. Okay. I think it's over to you now, Dave.
I think probably I'm on, yes. Okay. Take those away, please.
Just a little bit.
A little bit? Hello?
That's fine. Yeah.
Okay. Right. Is that the first time I've used a microphone here?
Just
Yeah, maybe, yeah. Okay. We're not on camera too, are we?
No.
I see a green flashing light over there. Okay. Right, as all of you except for the relatively newcomers know, I've been working for an extraordinary long time on this robotics project. The aim of this, and it was inspired by a young man who came along, it was about a year ago now, Amir, who's not here today, to try and run a course on, or a workshop or something on robotics to inspire young people. It's specifically aimed at young people. After a lot of to and fro, we homed in on sort of about a 13-year-old, give or take a little bit, age group, not the 8 or 9-year-olds who would be programming in Scratch, which is a graphical programming language, but kids old enough to have sort of gone past Scratch and want to get their teeth into a fairly serious or proper programming language. So I proceeded to design this little robot. At first we were going to use a commercial robot, but that was costing about $150 or something. I bought one for myself, which I'm going to use for my younger grandchildren. But I really wanted it to be something that was cheap enough for the kids to be able to keep at the end of the workshop so they could take it home and continue on this journey of discovery. So this one here, we're making this for about $40, and that includes a multimeter, a solderless plug breadboard, one servo motor, and a couple of other little bits and bobs, wires and things like that. So it's a very good value. It doesn't include the batteries. I've got to add that to the budget for the batteries. And so what I'm going to talk about is what I've been working on the last couple of weeks, basically, which is writing software to go in here to abstract or hide some of the hardware complexities from the kids, because we are talking about kids with short attention spans, and the fear is if we start to try getting them bogged down into real little intricacies of you've got to do this before you do that, or otherwise it's not going to happen, they're going to zone out pretty quickly because they do have short attention spans. So yeah, and there's the statement really that whatever length of workshop we have, there's never really going to be enough time to start teaching them on all the intricacies. I mean, I don't know, I spent probably years, younger years of acquiring the knowledge and ability to handle all this stuff and read a data sheet and find my way through it and so on. So a lot of finer detail inevitably has to be glossed over to keep the younger people encouraged and engaged and enthusiastic. The choice was made fairly early on to use one particular chip in this, and I've called the whole thing as a RoboMite. And the chip that I chose was the one called a MicroMite, which is a PIC chip that has been programmed with a BASIC interpreter. The BASIC, some of you were here a few weeks ago. We actually had the guy who wrote that BASIC. He's an Australian, called BASIC. And the more I looked at it, the more I thought, well, this is really close to ideal for what we want to do. The chip itself also, it comes in a dip package, so you can just plug it into a socket. There's no fine soldering with surface mount. It comes with the MM Basic. One of the features it has is that, take these kids, day 1, hour 1, lesson 1, and you can, and I'm going to actually go to this screen here, which is actually communicating with the board. I'll push the reset button, and you can see that I'm not communicating with the board, which is great. So I'll go back, hopefully connect. It always happens, doesn't it, when you go live? Okay. Right. So now you can see that we've got MM Basic version blah 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 beta 19. It's in beta at the moment because I actually requested some changes to the language from Jeff, the author of this language, and he accommodated me. And that made my job that I'm describing today a little bit easier than it would otherwise have been, which means I could do a slightly better job. And he has actually allowed, I haven't quite done that here, but yes, I have. He's actually given me permission to call the modified language that I've, with my extensions that I'm going to describe, to call it RoboMite Basic rather than MM Basic. So that's pretty cool too. I don't know how much we'll actually push that little point. Now I can, so imagine you're a 13-year-old kid, you just come in for the first time and you're given this board and it's plugged into a computer. Now I can just sit down here and I have to stop the program that's running. I can say print 5 plus 7 and it gives me an answer straight away. So right there, right from the very, very start, I can interact with this chip from a terminal without any extra stuff. Now you won't get that with Arduino or Raspberry Pi. Raspberry Pi may be with Python because you can have an immediate mode there too. But
what program are you running? Are you running a Micromite terminal program?
This is a IDE, Joe, development tool that's put out by some other guy called MMEdit. Yeah. It's a companion program that goes with it. You can also talk to this just through a straight-out terminal emulator, VT100 terminal emulator. I choose to use this this thing here because the editing in there gives you a bit of color coding and a few other things. You can auto indent and stuff like that, so it's a little more convenient. It knows the keywords. It's not the best IDE I've ever worked with, but it is an IDE and it's kind of okay. So I have this, and I think this is really important with the kids. Within a few minutes almost of sitting down, once we've got the cabling and stuff sorted out, they can interact with it straight away. They can do something like this, red light. Thank you. And it happens, that sort of thing. So now, if it's the first time you've done something like this, for you guys, you're old and crusty and what have you, and what. But if you're a 13-year-old kid, it's going to be, oh wow, hey, that's really cool. I think, I hope. Pardon?
Can you blink the red light?
No. Let me think about that one, Joe. Let me think about that one. It is no, it is technically possible to do that, but it becomes quite a little bit more complicated, as you well know. Yeah. Okay. Let me go back to my slides then. The chip, this is just outlining the chip really, but you've got this instant feedback possibility there. There's a good range of I/O features on this chip. It's a 28-pin chip, but it's got 19 input and output pins that can be, as with all modern chips, there's a lot of variability in how they can be configured. So there's a lot of flexibility there. There's quite a few analog inputs. I think there's 11 analog inputs, which is pretty radical. There's pulse width modulated outputs. There's 5 PWM outputs in total, in one group of 3, which matches up with the RGB LED, and one group of 2, which matches up with the motor speed control. There's SPI, ASC, there's UART, and what have you. The language itself has inbuilt commands for controlling the PWM outputs, for generating pulses, timed pulses, for measuring the interval between input pulses, measuring frequency, direct support for these cheap hobby-level ultrasonic ranges. It's just a command, boom, boom. What else? And commands for controlling servos. So there's a lot of stuff, obviously clearly hobby-oriented stuff built in to the chip already. The downside, or the problem is that those commands are somewhat more complicated than they might be because they allow you to use different pins depending on the mood of the day. So certain functions can be used, the ultrasonic sensor, the command for that, you've got to specify the pin that's used to trigger the sensor and the pin that's used to measure the pulse coming back. And so that adds a little level of complexity. But once the design of a particular board is frozen, then that flexibility is no longer needed. So for instance, with the ultrasonic sensor, I've made my own little wrap around that does the pins for you. So the kids don't even have to know which pins it's connected to. Just simplify it down that little bit further. And the other really, really nice feature is that with this chip, you can write a whole bundle of subroutines, and then you send it command, and it buries it under the hood in a library, often a separate part of memory. It effectively becomes an extension to the command set of the language itself, in a way that, I mean, if you're using an Arduino, you've got to actually invoke a library explicitly at the beginning of code. So you'd have to sit down with a room full of 13-year-olds and say, now, listen, little Johnny, before you can go, you've got to hash include this, hash include that, all this sort of stuff. With this, it's there. It's just going to be there, which I think is really a great feature of this particular chip and the way it's been implemented. Well, Joe, what are these chips worth? About $5 or something?
About $5.
Yeah. Yeah. Yep. Yep.
I'm talking about the one. Is this sort of like a custom chip?
Okay. Well, right. Okay. No, that's a good. No, that's a good question. One of the other possibilities would have been one that's called, I forget the name. What's another one of these chips that's got BASIC in it? Pickaxe. Thank you. No, it's a pickaxe. Pickaxe actually is bigger than this. It's very big, and you buy the chip with the BASIC already in it. The cheapest chip is about $18, and you cannot buy the core. What? Yeah, I think so. Yeah. No, but what am I going to do with an 8-pin chip, mate? Yeah, well, this, yeah. With this one, you just buy the PIC chip, plain, unprogrammed, plug it into a little adapter, and you zap it with this firmware, which is free. So the cost is $4 or $5 plus with the time. And the, yeah.
Any project trying to quality, cost and time,
Yep.
if you've got time, you can use
Yep.
any lower cost.
Yep. Yep.
Or you can buy the chip pre-programmed and sell it for chip for $15.
Yes, yes, yeah. But the pickaxe you can't. Pickaxe you have to buy it pre-programmed, so it's more proprietary.
These things run at 80 MIPS, they probably run at about 6 to 7 MIPS.
Right, okay, well, there's another factor, yeah. Oh, this thing is pretty quick. It's pretty quick. I mean, I've come from an 8-bit world with Tiny Basic running in 2K back in 1980 or 75. This is like, oh boy, this is heaven. This is, yeah, wonderful.
The basic that you've got in there, you've loaded or something.
Yes, yes, that's, well, actually Joe loaded it in, I think. Oh no, actually, no, I've updated it several times because we're up to beta 19. That's right, so Joe gave me the gear to do it.
You get empty chips, basically.
Yes, empty chips, yes, and you put it in. And you can make that programming rig basically on a breadboard, just a plug-in breadboard. A couple of components and you got it. And a USB to serial cable, which by the way in bulk costs $85 US from eBay. But so that ability to bury a library of routines under the hood is very, very powerful and really part of the game plan as well. So really this is pretty much the perfect choice for this project. And because the club is as a very special member, the price was really right too. Now, some of the complexities that...
If I seven bucks US for now on the full range.
Right, yeah. It does come in bigger pin-out variants, but they become surface mount, by the way. But, might dream of that for the next model of robot. You can see this group of pins here, 4, 5 and 6. They can be analogs, they can be digital, or they can be PWM group A, group 1. Now those 3 pins I have got wired to the LED, three color LED. I've also got them wired to the 3 servo connectors, and I've also got them wired to the loudspeaker. There's a little speaker on there. Now obviously you can only be using one of those things at a time. But that's again becomes really hard to explain to the kids, and you've got to have different parameters for the PWM, blah, 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 blah. So I've glossed over all that with instructions that basically, if you're using one, it shoves the other stuff out of the way. With the exception of the blue LED channel, which is on the speaker. So when the blue LED is lit up, you will hear a slight buzz in the speaker. But fortunately, it's not a 500 watt boom box, so it's not a real problem. So I had to sort of grapple with those, and again in designing the overall thing, that's the sort of compromise you have to make in design when you've got a finite number of pins. But I wanted as much functionality as possible. The motors are over here, left motor direction, right motor direction, PWM, which is speed. I've got a thermistor on here for temperature measurement and an LDR. And again, the LDR and thermistor, you select one or other with a little jumper. Gets a compromise because there's only X number of pins on the chip. So we've got some simple buried functions like set sound, and I can actually try and aim that at you.
Do you actually use temperature for anything?
No, look, a big part of the idea with this workshop thing was that we want to try and give the kids the understanding of the connection between sensors that sense what's going on in the real world, and then actuators which in turn affect the real world, because that is basically what robotics is interacting with the real world in an intended and unwanted way by using sensors and actuators. So, and in fact we're probably going to run an initial one-day workshop, which won't be the full deal, it'll be a one-day sort of 4-hour taster. We won't even give them wheels and motors, because the moment the wheels go on, it becomes a really fun toy. And everything else will go out the window. But they'll be doing temperature sensing, they'll be maybe making the speaker squawk a frequency according to the temperature, or something, whatever they want to do. Make the LED change color according to temperature. All that is possible. So they're getting that connection between the sensors and the actuators. It's a bit shy on actuators, you only get motors and an LED. You can plug a servo in, but what other actuators can you have? It's actually a difficult area. So if I go back to my little thing here. I can't remember if I stopped it or stop it. So set sound 2000. Can you hear it? Yeah. It's not loud enough to be too irritating to mum when little Johnny's playing at 10 o'clock at night. Far from it. In fact, I was actually toying with the idea of getting someone in this group to volunteer to make a little gizmo where you can put a microphone on there and amplify it up a little bit. So we're in this classroom situation. If little Freddie has come up with something that plays God Save the Queen or something, we can put it on that everyone can hear it.
I think we could use that.
Can you?
Yeah.
Oh, I barely can.
Really?
That's with my hearing aids on. In fact, I was playing with that a couple of nights ago with my hearing aids and started getting this really strange beat frequency. And I think it was setting the hearing aid off because the self-oscillation frequency is not too different. So when I do that, and I have to take my hearing aids out. I'm just doing it now. A particular angle of the ear, I actually get this modulation.
You've got one function there, you've got a set sound, you've got the clear sound, you've got to turn off.
Yeah. Again, the complexities are masked by that little routine. And you probably saw the blue light coming on too. Yeah.
So then my next question would be, if I only wanted the sound on to go on for one second, is there a function for that?
No,
Not yet.
no.
Okay.
You're a bugger. Look, I've been skirting around this whole thing because now you still got to have some background multi-processing going on and what have you, and yeah. But this chip actually, that was a very good question, Joe, because this chip actually does support the concept of having a periodic timer interrupt where it will go off and you can do stuff and come back again. You can have, I think, 4 or 8 of those little timer interrupts. So you can actually get multitasking happening without having to build a complete multitasking subsystem if you can live within a certain set of constraints.
Oh, Microsoft Basic never did background processing for sound though. You might as well just halt execution while you play your tone for a second and then return.
Well, it depends. If you're about to fall off the end of the table, that might be a problem, but yeah. Yeah, yeah. Yeah. Look, I don't think we're going to get the kids into the subtleties of multitasking and deterministic programming or recursive code or anything like that. But yeah, that's why we probably won't be solving mazes because that's going to be yeah. Solving a track like that would be about the limit, I think. So we've got that. The other one, and this is actually pretty much where it started, there's a thermistor there. So I can just type get therm, a question mark as in all basics is an abbreviation for print, by the way. Print get therm, and it's 20.8 degrees on that thermistor at the moment. I can do this, I can do print get therm. Try not to make a typo, there's a lot of stuff here. Pause 500. Loop. Copy it just in case. Now, how easy is that for a kid coming first time? He can get a result without him having actually written a program. But he has written a program. He just doesn't know it. And if I put my finger on there and heat the thing up, you see the temperature going up. You can actually, with this, and it took me a little while to figure out what's going on, when it first gets turned on, you can actually see the thermistor self-heating by about 0.3 or 4 of a degree. Because when I designed this, I didn't, even if I'd thought of it, there was not enough I/O on the chip to just switch that circuit on ever so briefly, take a reading and switch it back off again and get out of there, which is what I would have done in a more professional sort of environment to guard against that self-heating. So, let's stop that. So those are the simple buried functions, but are they really that simple? set sound, it actually does a couple of things other than this line here, I can't highlight it, which sets the sound. It makes a call to another routine which turns off the other channels. If we're going to play sound, we better turn off the other two channels. And then it sets the sound. For the thermistor, that's the thermistor equation. Now, I don't think you're going to get a room of 13-year-olds to try and solve that and start coding it. So I've done that. I've actually done it with, and I'm not going to even tell them about a 6-order polynomial derived from Excel either, but that's what I've done. It's something I've been doing many times through my career with thermistors. I imagine you can hear me okay? Is this thing working? Is it? Yeah, okay, good. So even those simple ones have got a little bit of complexity. I've got one for I've got a number of things for setting the color LED. This one was probably one of the first ones I did. Set RGB with red, green and blue values. And because traditionally with RGB you have values from 0 to 255, that's how I scale it. Whereas the native PWM command expects values from 0 to 100. So again, just to sort of try and get them into the right right sort of thought pattern, and it just quietly sets the frequency to 50 Hertz, which is about optimum for not flashing the light too much and that sort of thing to avoid strobing. So I can give an example. Set RGB to 100, say 0, 200. You learn to always copy a command before you hit enter. And you may hear the speaker. That's the little 50 Hertz thing. But, yeah, a little rattle. I can change that to 100, and of course get a different colour. If I set them all equal, I get about white. So they're going to learn a little bit about colour mixing at the same time. So we're trying to sort of tackle a few little different areas as well, of physics and what have you. Right, okay, yeah. Yeah. If I go set RGB without anything, I think that turns it off, yeah. Because the nature of this particular basic language is if you don't have the parameter, it sticks it in as 0. So just take advantage of that. Ah yes, notice, as far as the kids are concerned, there's never been any mention of PWM, pulse width modulation. It's a complicated concept for somebody who's coming in absolutely raw. And it would take probably 1 3-hour session, we need oscilloscopes and all kinds of stuff to start to get that message through. So that's completely covered over. They don't need to know about it. I really want to try and keep the focus on the more creative aspects of using this to follow a line or find your way around the table and not fall off the edge and avoid blocks and obstacles and stuff with the ultrasonic sensor.
I would say you're abstracting the complexity.
Yes, yeah, it's another level of abstraction, exactly. Which C famously fails to do. Oops, wrong one. Some more LED control ones, because I do have an LED there and it's fun. So these set red, set green, set blue, they control the individual LEDs, but setting one doesn't change the others. Again, so we're intervening under the hood because the actual native command for PWM, for the 3-channel PWM, if you want to change the last one, you've got to provide the values for the first two as well. So for the sort of A, B, and C, you've got to do, if you want to do C, you've got to provide the numbers for A and B. But what I do is I just, whenever it's called, I squirrel those numbers away under the hood, and then when it's time to update, I pull them back out. That was actually the feature that I asked Jeff to do for me, is to have static variables within functions and subroutines, so they're preserved. So I've still had to use a few global variables, unfortunately, and I hate having to do that. And it's one of the more messier aspects of this basic, but at least I give them weird names that they're never going to stumble into. Sort of underscore, dot, underscore, or something or other names. And then I got the really primitive red light, magenta light, cyan light, etc. So they've got many options for. Yes, yeah. I've got the three primaries and the three additives and the three subtractives. Yep. And
You put the cyan on.
yeah.
If you go and shop on eBay for cyan, you'll end up getting green.
Oh no. It's cyan. Yeah.
You try to buy one of those LEDs.
Oh.
I mean, a LED.
Oh, because that'll be a single dye lead, and they can't really get it. It'll be emerald green or something like that. Yeah. But with RGB LEDs being so cheap, I'm not sure why they even bother with making different coloured LEDs these days.
Well, the other ones that come through a LED plate.
Yeah, easier to ride. So what was it? Oh, turn off. So we've got those. Servo. Now the same PWMs come out to three pin headers here, so you can have up to 3 servos being driven off it. And I'll plug that in. I'll plug it into number 1, which is the second one, just for fun. The correct way around, otherwise smoke would come out very quickly. And I didn't bring along a stand or anything for that. You just have to watch very carefully. So set servo, that's number 1. They go 0, 1 and 2 to 180. Save it. That's 180 degrees. If I set it to 1 degree, it's back the other way, so it's very easy. So I've taken care of the scaling and all that sort of stuff under the hood, so for this particular type of El Cheapo servo, it kind of works okay. There is a problem with these El Cheapo servos. If you start driving up against the end stop, they start to use up battery power really quickly, and they actually can get warm. So I wouldn't ever use those, I think, and Rob would second this, I'm sure, never use these for a serious project, because he likes to pay $50 each for his servos, doesn't he? In fact, just feel compelled to. Now, unfortunately, I'm a bit limited because I went to replace this thing last night, which I did successfully. The ultrasonic sensor wasn't working, and I only discovered when I came in just now. In doing so, I broke the line sensors. It's got 2 photoreflective sensors here that send out infrared light and then measure what's reflected back. And I've had a lot of fun and games with that. The lines on this track are exactly 22 millimeters wide, which is the pitch between there, so that when it's dead centered on the line, they're going to be at about the halfway mark. Now, when I started doing this, the first thing I did is I printed out a test track on my inkjet printer at home. Guess how much infrared light the black ink out of an inkjet printer absorbs? Nothing. Nothing. I'm going to bounce that straight back at you. No reading at all off a black inkjet printer. Canon brand, with cheap cartridges bought from eBay. Nothing. Not a peep. So I went to the $2 shop up at on the corner where I live, and I bought a nice fat texter, and that was beautiful. So for a while I was printing out just an outline and then filling it in with this big fat texter. Then I discovered that it was actually conceivably possible to have white, black ink and black hole. So you may have, I had this in here a few months ago, and I was actually allowing it, sorry, this is wrong, allowing it to run off the edge of the desk and then stop, because it was seeing total absorption of light. So I mucked around a little bit with that as well, and found that a Sharpie brand pen will give it sort of intermediate absorption of infrared light, whereas a black hole is basically infinite absorption of black light. So for a while I was sort of using Sharpies, but I thought, no, it's just too hard. So recently I got Marlin in the office to print out some stuff on the laser printer in the office, and it's good. So that's very high absorption, but in the process of all that, I started thinking, well, I know that these things are cheap from China, there's going to be variability between them and all this sort of stuff. How can I handle that without the kids winding up with just total and utter confusion? And the idea I came up with was basically to have automatic calibration of the line sensor. So what we do is we have this little black patch here, and you'll see one on that track as well. You position the robot on that track, and at the moment I've got some remote control set up here, but it's broken. It takes a reading. In fact, the auto calibration, it takes 10 readings and averages them, and then it moves forward a little bit on its own. So it's on the white paper, takes another set of readings, then it does some sums and works out the coefficients and offset just for a linear fit, so that black is going to be 0.2 and white is going to be 0.8. And then there's a little bit of headroom either way. Somewhere between, say, probably 0.4 and 0.6 is going to be, well, I'm not really sure what's going on here, sort of territory. But that way you can get equalize all the differences between sensors and, to some extent, inks. I have noticed if the paper's a bit curly, it can actually reflect at one stage, and I'm trying to iron this bloody thing flat. But yeah, it's easier to come in and get them printed here. So that's sort of how it's going to be, I think. And that calibration has actually been quite successful, and I can't demonstrate it properly because the line sensor's broken.
So the reason you already kind of cheaper than proper light sensors?
No, they're proper light sensors. There's nothing improper about them.
In the visible rather than because I mean, invisible, black is black.
Look, okay, look, what's the word? Lateral thinking solution to the problem, if we consider a problem, might have been to actually say, well, I'm going to pull out the infrared LEDs and stick in 3mm red LEDs, or green LEDs, or what have you, or blue LEDs even, because they're all so dirt cheap. White LEDs, but to be honest, I didn't even think of that.
Oh, this is not, you're not using an infrared light sensor, you're using lens on
Now this device, it actually consists of an infrared LED, which is rather blue. We'll pass it around. Slightly blue, and an infrared phototransistor, which is the one that's got quite a black case, because it's got an infrared filter on it. And the infrared LED is just on. Now, again, if I'd been designing this professionally, I would be pulsing the infrared light on and off, and I'd be measuring the distance between the received signal with it on and the received signal with it off. That way it would filter out any ambient light. So this thing, because it's done on the chip, well, it's done simply because I only had a certain number of pins on the chip. It can be full. If I sort of calibrate it there and then turn the ambient lights off, it might upset the calibration somewhat. Or if I had a light coming in at a sharp angle and the robot turns around, it might upset it. But that's a compromise you just have to live with when you're trying to get down to $40 for the whole thing.
So you're actually using infrared, you're emitting infrared
Yeah.
and reading
Yeah. Yeah. No, I just bought these sensors. The original one that I went after is one I'd used for over many, many years in my career, called the CNY70 from Telefunken. And I bought one or two of those for about 60 or 70 cents each or something. And then I discovered these, which are less than peanuts. And they work fine.
That, if you're using black paint, which is basically black and visible, you don't know whether it's black in infrared.
Well, that's exactly the problem I encountered with the different inks, my printer ink and the different textures. Fortunately, I mean, these laser things are carbon-based or something or other like that, and it absorbs pretty well, pretty solidly. Yeah.
The sharp infrared data sheet spec have a set of colour cards, grey, white, grey, and dark and black.
Yep.
And that's how they define their spectral pictures. So actually, by the grey, the shade of grey and reflection of these set of cards they have as their reference standard, so they can go across all the production line with all these cards.
Yes, but the ink on those cards still has to be infrared absorbing.
Yep.
Whereas the ink in my printer is not infrared absorbing. To the eyes, it absorbs visible light.
That's the whole point, is that the paint that you need to use on these things needs to be infrared absorbing.
Yes, yes.
Rather than
it needs to be controlled.
yeah.
There needs to be control that end as well as that end.
Yeah, it doesn't
Yep.
really matter what colour it is in the visible,
No,
as long
no.
as you can see it.
Correct. Yep. So that's the line center calibration. That's something I've done sort of in the last week or so. That's been quite successful. Okay, finally, this is the last one. The actual control of the motor speed. The motor, each motor is driven by two outputs. One which is direction, which basically reverses the polarity. It's got a bridge driver, and speed, which is pulse width modulated. How to wrap that up into a simple function that kids can use. Now, at first I wrote a primitive one where you had to sort of set the PWMs and everything yourself, and I did actually have a successful line follower using that, but very complicated to use. So the scheme I came up with is that for each motor you have to specify speed, necessarily, and direction, unless you want to just go full bore, which is not terribly fast for this, by the way. That's another design compromise, which I can discuss if you're interested. But so I said, okay, what I'm going to do is I'm going to define. I sort of thought in terms of compass directions and things. If the thing is steering directly in a straight line, I call that direction 0. Now, there's no precedent for this all the way. This is just something I just kind of came up with. If I have direction -1, it means that the right wheel is going at full tilt and the left wheel is stopped. So it's going to go around like that. If I have it at -0.5, the right wheel is going to go at twice the speed of the left wheel, so it will go in an arc like that. This diagram is a little misleading. It's not the direction it's going to go in, it's the derivative direction, really. So it's going to go around in a curve, sharper or slacker. If you go past -1, you have the right wheel going forward and the left wheel going backwards, until you get all the way to -2, where the thing is literally spinning around the wheels on the spot. And the same going on the other side. If you go to +0.5, it's veering around to the right. +1 is going quite sharply. In fact, it's spinning on that right wheel, and so on, and to +2, where it's spinning around the wheels like that. So it does have all those movements, and maybe more by us than by class, it works out if you just reverse the direction, going like that, you as the speed. If you change the speed from +1 to -1, it will go back over the same trajectory. So it's continuous and smooth and predictable. And that took many, many days. many days because I had to make a table in Excel of what I wanted to be happening with different numbers, scratch my head, find the equation, okay, we're in this quadrant, we're in that quadrant, blah, 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 and put the code together, which in the end looks deceptively simple. But the amount of work that went into it, yeah.
The values of D, you can have, those are, they're not integers, so
No, they're floats.
they're floats.
Yes.
And you can have any number between 0 and
Minus 2. Minus 2 and plus 2.
-2. Oh, plus 2 is just the other way.
Yeah, minus is to the left and plus is to the right.
So you get, instead of curving like this, you get curved on different arcs by having
Yes.
D equals 0.7 for example.
Yes. Yeah. Yeah.
It's very clever. I find it confusing. But you want it not confusing for a 13-year-old. In maths, we already have magnitude and we have polarity. I must admit, I don't see why you just don't use it one for each wheel. Why not have positive direction and negative direction and magnitude for each? I think it seems logical, I must admit.
It ties in, Gavin, with the line following thing. And it turns out with this, the line following algorithm is basically if you take the ratio between the two sensors and apply that to the D parameter with a multiplier, gain factor, you've got your line follow within certain limits. I mean, there are certain points where that's going to fall apart and you've got to pick those cases up as well.
Got a suggestion for you.
Yeah.
It's going to be more work. I think
You know where I live, Joe? Just come round and help out. Yeah.
all you need to do, I think, to get this visually into the kid's mind is to do 3 or 4 examples, videotape 3 or 4 examples, and he or she will get it.
Yeah.
I think, you know, if it tells 1,000 words, but a video tells 1,000,000 words,
Yes. Yes.
do it in
Yep.
3 minutes video,
Yep.
type this value in, it does this,
Yep.
type this value,
Yep.
it does that, and by about the 5 minutes, the concept, all those things with the visuals,
Yes.
with the, to see the
Yes.
terms
Yeah.
in the art,
Yeah.
I think you'll say,
Yep. Yeah.
you won't have to type a whole page.
Yeah. Yeah. Yeah.
That might be
Yeah. Yeah, and I struggle a little bit in making this slide for pretty much kind of that reason, because this is suggesting a static direction rather than a trajectory.
Yeah, where video would show that.
And I thought, well, maybe I could make it. Oh, no. Bloody Wednesday night, I can't be bothered.
Well, if I get
But-
past that from wife, I'll bring the camera around and we can
We'll do something, yeah.
bring
Yeah.
the camera around. We can just
Yep.
record the file and just
Look, it can also be demonstrated live. If I can, Bill, if I can have that. Well, I don't have a camera on this thing, but you can possibly see it. Thanks. Actually, one of the things I haven't included in this little show is the remote control, which I learned. But I can do that. Now I can start turning it left. And you can see now it's at -1. And I go further. And now it's at -2. And I can reverse the direction as well with the buttons here, and I can, the other thing I can do, I've got a button to make it continue straight, reverse it. Now I can make it go like that. Whoops, that's too aggressive.
That's only you adjusting the value of D.
That's me adjusting, and that's the velocity now, but that's D. If I reverse direction, it goes back over the same track, which I think is actually important because it gives that total symmetry to the whole thing. As you can see, it's not very fast. That lack of speed, basically the whole mechanical design of the thing is dictated by those line sensors, because they work optimally at a certain distance from the target. And pretty much everything else follows. They're a very extreme extension of the leads they come with, and short of extending the leads somehow and making it a lot harder to build 40 of these boards, that was kind of what I was stuck with. The size of the wheels follows. The motors come with a gearbox that they come with. The only way you can make them go faster is to ump up the voltage, and that ain't going to happen. So that dictated a lot of the design, that sensor. Okay, I haven't included it in this lot. Yeah, there's the sort of direction symmetry with an imperfect, that line there is imperfect shape for what it's trying to illustrate.
You have a basic function for that. You have a basic function for that.
Ah, yes, yes. I can show you that. Let's see
I
whether-
don't need to know the underlying deep level, but what the kids might see as a function.
Yeah, well, they just see something which is, well, there's my whole line follow code there, using these things, and there's the call to the function, set, move, speed and direction, and an optional parameter there which actually will indicate on the LED where it's going, just for a little bit of feedback. Sorry about that. How's that?
Yeah, nearly right. Just up a little bit, so it's on your
Oh, okay. I'm seeing things. Okay. Oh, that's loud. Yeah, that's sort of pretty much what I have for you, I think. Yep. That's the last show, last slide. So, any other questions? We're going for time. 8:30.
What age group?
The nominal age is 13. So it's going to be sort of 11, or 12, 13, 14 maybe, or maybe 13 a bit down. It's a bit hard. We don't know who's going to be interested yet.
And you'll set up in the beginning in the laptop program. What do the kids need to do to achieve that?
Very good question. And I will be calling for volunteers for the first session, for as many as possible from this group, because there is no way there's not going to be problems getting that going. Because you've got to go into the program and you've got to find what COM port it is mapped to and all that sort of stuff, and that's always a problem. So that first little bit of actually getting to talk to the board is almost the biggest hurdle, but there's no avoiding it.
Yeah, can I comment there? Different people have different personalities.
Well, I thought I was seeing double there for a moment.
Different people have different personalities, and one of my observations is when you've got a group who are doing an activity all in parallel, some people with a personality are not prepared to say, I didn't understand that, I haven't got it going.
Mm-hmm.
So the first 5 minutes, they're completely silent, and from that point on, they've lost it because they're not getting to square one. They've got nothing going, and everything that's said up front is lost on them because they're still trying to get the first bit going. So I think what you said is really important.
Yeah, all they've got to
There
get.
needs to be enough help around
Yep.
that each
Yep.
involved
Yep.
gets somewhere quickly,
Yes.
not stuffing around for half an hour.
Yep. Yep.
If I put
Yes.
it to someone, you end up managing people's laptops for the first hour or so.
Yes.
They've got their own
Yeah.
Yes.
Because
Yes.
each one has a different USB driver, there's virus programs, and
Yep.
other hardware dependencies.
Yes.
You end up managing people's laptops because you have a USB device.
Yep.
So it's a Bluetooth device or a Wi-Fi device, you end up managing people's laptops.
Yeah.
So it might be, depending on a pre-session warm-up to get the half an hour session before or something
Yeah.
to get that
Yep.
yes,
Yeah. Yeah. Yep. 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 Yep.
Yeah.
Yep.
The session might be heroes running around, you found out there was a lot of hardware dependencies.
Yeah, absolutely, inevitably, absolutely. Unless we had the luxury of I actually had sort of eyed off the training room, and so I was thinking, well, we could actually have a computer set up. Problem with the training room is there's 2 computers on each desk. There's actually no space for the actual thing. So unless we were prepared to manhandle half the computers out of there and back in again, I guess afterwards, we can't use a training room.
Would be a better option because then you know you've
Got a standardised.
standardised platform to start with.
Unfortunately, that mitigates against the kids being able to take their robots home. So you kind of, it's a lose-lose or win, whatever you call it, because they need to have those problems sorted. And I'm quite insistent that they get to keep the robot. Not after the one-day seminar, no, but after, if they're going to be a 5 or 10 week Sol workshop series, yeah, they've got to be able to take it home, because there's a lot more exploration to do on this than we'll cover in that time.
Most kids have their own computers anyway, laptops. It's part of the curriculum.
Oh, yeah, no. What we're debating is about whether we tell them to bring their own Windows 10 computer with this software pre-installed. That's just got to be a no-brainer. Or whether we give them a working computer when they get here. If they're going to be able to take that home, they've got to be able to take home working who's you whatsy. Yeah. Yes. Sorry? Oh, well, no, bad luck. Bad luck. Well, whatever they want to do is... Oh, shit.
Absolutely.
Can you just imagine getting USB to work on Windows on a Mac? Oh, God. With virtual COM driver stuff? No, we do it different. At Apple, we have Bluetooth LE, don't we? No.
The chip, the big chip, I think it is, that's got the USB on it.
No, it's serial. It's UART. So this is a UART to serial, USB to UART there, yeah.
And they all the same, are they? Same chip on same USB.
Oh, I bought 40 of these cables.
Sorry?
I got it. Yep. Oh, I wouldn't leave that to chance. No way. Sorry? Who was that? No? That was a very loud think.
It's creaking. Serial to Bluetooth adapter.
Grrr.
Yeah, I know.
No. Joe is or was going to talk about Bluetooth on here, and I won't say I didn't consider it, but I only consider it for the shortest amount of time, because I have personally I've managed to get Android devices to connect to Bluetooth adapters. I've never managed to get my PC to connect to one of these little hobby level, whether I'm doing something wrong or not, but that's just another bloody hurdle. He's good. His cable. Yeah. Yeah. And I'd love to have it wireless. Love to have it wireless so I can monitor the thing as it's trundling around the table and sending back diagnostics. And the best I can do at the moment is sort of like that. Or have the light flashing little codes or something like that. I'd love to have wireless, but... what you mean for the... I think these things